Chapter 10, Structure and Synthesis of Alcohols. We will learn how to name alcohols. We will look at physical properties, and we'll see synthesis of alcohols and methods of prep, how we can make those alcohol structures. The following chapter will discuss reactions of alcohols. So alcohol structure usually has a hydroxy group, and it's very common organic compound that you will find OH to be part of it, as it exists in a lot of biological active compounds and structures that are used in industry and around the house. You can see here examples of those alcohols going from ethanol to methanol to rubbing alcohol, which is isopropyl alcohol. The structure of alcohol is very similar to water when it comes to the bond angle and the intermolecular forces that they usually form. So when you look at the water molecule, have a bond angle of 104.5. So it's a tetrahedral shaped compound, but because of the two lone pairs, they push down the bond angle to be 104.5, less than 109.5. Now, when it goes to the alcohol structure, because of the atomic size of the carbon atom, bigger than hydrogen, that's going to actually make it a more relaxed bond angle. So that's why you see it increase to 108, 108.9. So that's important to keep in mind. Now, the intermolecular forces will be very same. So we'll talk about that in a minute. Now, classification of alcohol. It's very important that we are able to recognize what type of alcohol we're dealing with. Is it primary? Is it secondary? Is it tertiary? Or is it an aromatic alcohol? Now, those primary alcohols usually have a carbon that's attached to another. So there is only a single carbon attached to that COH. And remember, the COH classification is what's going to determine the classification of alcohol. So looking at the secondary alcohol, what do we have? We have a carbon attached to OH. That's a secondary carbon because it's attached to two other carbons. And again, one carbon attached to that COH makes it a primary. Two carbons attached to that COH makes it a secondary. And that is the same for the tertiary. When you have a carbon attached to three other carbons, that makes it a tertiary carbon. Therefore, that COH now, it's a tertiary alcohol. And finally, the last classification is when you have an OH attached to a phenyl. So that's an aromatic compound. So that's an aromatic alcohol. So that's phenol as an example. IUPAC. The first rule, usually in IUPAC set of rules, is that to find the longest chain of carbons. But in this case, because we have an alcohol group, we have to have that longest chain of carbons that has the OH part of it. And once you find that, that will be the parent name. So the alkane becomes an alkanol. So you take the E off and you insert an OL. And in making sure that we insert the locant, the position of the OH within the parent name. So you're going to have to say alkane and the position, ol, the position of that OH. So let's look at examples. So the very first one, it's ethanol. So there's no need to say F1ol, but obviously because the OH is going to be on one of the two carbons, so it's not going to make a difference to put a number there. This structure right here, what do we have? We have carbon number 1, that's where the OH is. Carbon number 2, that's where the methyl is. And carbon number 3, so that corresponds to propanol. Now, how would I name the structure? Well, the substituent will be first, so that's 2-methyl, and then propane 1-ol. So be careful not to insert the E, because that E already been replaced with OL. Cyclohexanol, these are actually put in a way that they are based on classification. So they're giving you examples based on that. So here's a benzyl alcohol, just like phenol. You could say phenyl alcohol, or you could say phenol. So either of the two is acceptable. Here's another example. So we have 1, 2, 3, 4. So this is 6-butanol, or the IUPAC name would be butane 2-ol. So either of the two will be acceptable as a name, but the IUPAC name should be butane 2-ol. Cyclohexanol, and you have now 1, 2, 1, 2, 3. So that's 3 carbon chain has an OH on carbon number 2 and has a methyl on carbon number 2 as well. So that's a 2-methyl propane 2-ol. So always find the longest chain of carbons that has the OH part of. So instead of saying 2-carbon chain, it's actually 3-carbon chain the OH is part of. Here's a triphenyl methanol. Here's a 1-methyl cyclopentanol. You don't need to insert the 1 for the alcohol when it's on a cyclic alkane, because by default, it's got to be carbon number 1. And phenol, usually when there is a substituted phenol, you're going to always have to give the carbon number 1 where the OH is attached to be number 1. And number 2 would be the next, 3 where the substituent is. So that makes it a 3-methyl phenol, 3-methyl phenol. Here's a 1,4-dihydroxy benzene, or the common name for it, hydroquinone. So 1,4-dihydroxy benzene. What if there's other functional groups in the structure? Now, it's important to keep in mind that this priority has to be applied. For now, we're going to learn only about alkenes, alkynes, alcohols, and acids. Acids usually the highest in priority. Next would be alcohols. Next would be alkenes, followed by alkynes. You could see here that alkanes, ethers, and halides are lower in priority when we compare them to alkenes and alkynes. So if I have an alkene and an alcohol, the alcohol will be given the priority. So the chain will be numbered from the side that's closest to the OH. So here's 1, 2, 3, 4, 5. So carbon number 2 where the alcohol is, and carbon number 4 where the alkene is. The name should sound as alkenol, alkenol. So the alkene has to have a locant where it is, and the alcohol has to have a locant where it is. So here it is, the name pent-4-ene, indicating the pentene where the alkene is, that's carbon number 4. And at the end, you have 2-ol, that's where basically the alcohol is. And this E shouldn't have been there, actually. This second E shouldn't have been there. So pent-4-enol, there is no E in here. So it should sound as enol right away, enol. So the correct name should be pent-4-ene 2-ol for this structure. Here is a carboxylic acid with an alcohol present. Carboxylic acid gets a priority. So you number the chain from the side where the carbonyl of the acid is. So here's 1, 2, 3, 4. That in that case, the alcohol becomes a substituent. The substituent becomes hydroxy. What is the name for this structure? 4-hydroxybutanoic acid. 4-hydroxybutanoic acid. This gamma, it refers to the alpha carbon. That's the carbon next to the carbonyl. Beta will be the second carbon away. The third carbon will be basically the gamma. Here is some common names and their corresponding IUPAC. So the first one is the isobutyl alcohol. That's the common name. The IUPAC name would be 1, 2. So that's 2-methyl propane 1-ol. 6-butyl alcohol. That's the common name. The IUPAC name would be 1, 2, 3, 4. So that's butane 2-ol. Butane 2-ol. What if I have a diol? The numbering will still be the same, so it doesn't matter which carbon you start with, unless there is a substituent on the chain that will be determining which side to start with. Obviously, you want to give the substituent the lower numbering in that case. Now, in this structure, we have 6-carbon chain and OH on both ends. The name would be hexane 1,6-diol. So when you use diol in the end of the name, remember the E, it's still there. So alkane, the locants for those 2 OHs, and then diol. Here's more examples. So this is ethylene glycol. That's the common name. The IUPAC name would be ethane 1,2-diol. Here's 1, 2, 3. So that's a 3-carbon chain. So that's a propylene glycol common name. The IUPAC name is propane 1,2-diol. You're always going to be asked to give the IUPAC name, but it's important to keep those common names in mind in case you are coming across those names in the homework assignments or in your reading material. These are substituted phenols. So we already talked about this. This is the 3-chlorophenol. So you always, when you have a substituted phenol, the carbon attached to the OH will be carbon number 1, because you're going to be numbering the benzene ring. So carbon number 1 will be the COH, and then you go toward the next substituent to give the lowest numbering for those substituents. So this would become 3-chlorophenol. Now, this would be 4-methylphenol. Now, there's other systems that's ortho, meta, and para. Ortho refers to the carbon that's adjacent to the COH. Meta is referring to the 3rd carbon. So this carbon is the 1st carbon that's attached to the OH, the 2nd and the 3rd. So that when that substituent is sitting on carbon number 3, that position is called meta. And the 4th position, 1, 2, 3, 4, this is called para position. So the common name, which is also acceptable as an IUPAC name, is when you say ortho bromophenol, meta chlorophenol, para methylphenol. So these are acceptable common names and IUPAC names, not paracresol though, because this is a common name that's more of a generic name rather than it's actually an IUPAC that's using para system. So ortho, meta, and para, they become more applicable when we look at these structures later on in the benzene compounds chapter and their reactions, and that will be in the following course. Here's an example. So you could see the longest chain of carbons is actually where the OH is part of. That goes from right here all the way down. So 1, 2, 3, 4, 5. So that's 5-carbon chain with the OH is attached to the 1st carbon. And what do I have? Carbon number 2, I have an isopropyl. And carbon number 3, I have an iodomethyl. So the name would be basically 3-iodomethyl in parentheses because it's a complex substituent. That's why you have them in parentheses. And then 2-isopropyl pentane 1-O. And that's the IUPAC name. Physical properties. Now, it's important that we remember the intermolecular forces type that those alcohol molecules form. And all of them usually tend to have hydrogen bonding. That's why the physical properties are actually influenced by that type of intermolecular forces. And when we say physical properties, we're talking about boiling point, melting point, and solubility. The bigger the chain, the higher the boiling point or the melting point. And not only that, the smaller alcohols usually more miscible with water compared to the larger ones. So the alkyl chain, the longer it is, the less miscible. It may become actually insoluble in water. That's usually the trend. So looking at this table could tell you actually that the trend, once again, the longer the chain of alcohol, the less soluble it is in water, and the higher the boiling point or melting point. So they could see clearly here that the alkane compared to the ether compared to the alcohol. Alkanes usually have the London dispersion forces. That's why the boiling point and melting point usually are very low. Ethers, because they have dipole intermolecular forces, they don't have the power to form hydrogen bonding with one another. That's why the boiling point and melting point, they are lower than what alcohols and water do. You can see here clearly that the hydrogen bonding could be actually between not just the hydrogen and the oxygen, could be the oxygen of the same molecule that formed already a hydrogen bond with another molecule of the same. So this hydrogen becomes part of a hydrogen bond, and the same molecule, oxygen, can also be part of another hydrogen bonding. And this is just examples where it shows you that the alkyl group, the bulkier it is or the longer it is, the solubility in water will be affected. So it becomes less soluble the more carbons attached to that OH. Here's some examples of alcohols that usually made from nature. So we could see here that you have the methanol that we refer to as wood alcohol. Usually they make it from carbon monoxide and 2 hydrogen. So you reduce the carbon monoxide to form methanol. That's the industrial application, actually. That's how they make methanol. So CO plus 2H2 in the presence of zinc oxide and chromium oxide. These are usually as the catalysts to reduce the carbon monoxide to CH3OH. See here, ethanol, that's also used as a fuel agent. So we could see here that some other properties that usually are in there. Ethanol is also known to be a common solvent in organic labs. Here's the rubbing alcohol. So when you take propylene and you do the water hydration of that, so that gives you basically the access to rubbing alcohol. Acidity of alcohols, all of them, they tend to be in the range of 16 to 18. 16 to 18. So water has a pKa value of about 15.7. Alcohol very close to it, so it may be a little slightly more acidic. But again, the more substituted the carbon, the OH is attached to, the higher the pKa. So if I look at this structure, this table, you can see here, methanol is 15.5. Longer, that's ethanol, the pKa gets higher. And if I look at isopropyl alcohol, it's higher and higher. Terbutyl alcohol is 18. So it gets weaker and weaker in terms of acidity, the more substituted the carbon is that's attached to the OH. Now, inductive effect, such as having an electronegative atom attached, which is 2-chloroethanol as an example. Ethanol has a pKa of 15.9. 2-chloroethanol has 14.3. So that inductive effect weakens the bond between oxygen and hydrogen. That makes the hydrogen is easier to abstract it because the electron density now is being pulled toward the electronegative atom. You could see here the cyclohexanol is 18, but if I make it a aromatic ring, which is phenol, it goes 10. So that's 100 million times more acidic than cyclohexanol. And there is a reason behind that. So when you look at the structure of phenol, comparing it to cyclohexanol, the conjugate base is more stabilized when you have the phenol being deprotonated, and we'll see that in a second. Now, usually the alcohol, in order for us to generate the anion or the alkoxide, we use sodium or lithium or sodium hydride. So whether you use sodium metal or potassium metal or lithium metal or the hydride reagent, which is sodium hydride or lithium hydride or potassium hydride, these are strong bases, can also be used. Now, all of these reactions, they generate the alkoxide and the hydrogen molecule. So that's how favorable the reaction is. It generates basically a gas that makes it so hard to be reversible. It's not going to be giving you a chance to get back to the alcohol structure. So this alkoxide can be used basically as common bases or could be used as strong nucleophiles. Because when we go back to the nucleophilic substitution chapter, the alcohol is ranked as a weak nucleophile. But if we deprotonate the alcohol and make an alkoxide, that jumps to become a strong nucleophile. And those strong nucleophiles are not just acting as nucleophiles, they could be also acting as bases, strong bases. Depending on how sterically hindered the alkyl halide, they can do elimination rather than substitution. And this is the phenol that I was just talking about in presence of a hydroxide that's going to generate the phenoxide. So the pKa of phenol is 10. pKa of conjugate acid is 15.7. We already know that acid-base reactions, they exist in equilibrium. They are usually favoring the higher pKa side, the weaker acid. So the reason why this favors the phenoxide formation is because of the stabilization effect, resonance stabilization of the conjugate base. And here it is. So you have an O minus, that's the phenoxide. O minus gets delocalizing toward the ring, so that makes a negative charge now on the orthocarbon, pushed back to form a double bond, puts it on the para, goes back and forms a double bond to give you the other orthocarbon ion. So the four resonance forms what contributes to the stability of the conjugate base, and that conjugate base now becomes a weaker in terms of basicity, and that corresponds to the acid to become a much stronger acid. So this is a picture I need to remember when I'm comparing cyclohexanol to phenol, because the only difference between the two is the aromaticity within the ring. So I have a benzene versus cyclohexyl. Alcohols usually are made from other functional groups. We've seen some of these reactions in previous chapters. So the very common functional group is the alkene, but before the alkene, we could look at the nucleophilic substitution pathway, and that's starting with the alkyl halide. Now, the alkyl halide, if it's a methyl halide or a primary halide, that's a chance to give me an alcohol through an SN2 reaction. Because if I have a hydroxide or an alkoxide attacking a secondary alkyl halide or a tertiary alkyl halide, the higher chance is going to give me an elimination product, an alkene rather. So that's important to keep in mind. Addition of water to an alkene usually gives me an alcohol. So those reactions we learned in the alkene chapter, one gives me the anti-Markovnikov addition product, and two of them gives me the Markovnikov addition product. The first one, which is the anti-Markovnikov, is through hydroboration oxidation. And just to remind you of the condition, the first step is BH3 water, and the second step is hydrogen BH3 THF to add basically the BH2 on the less substituted carbon, and the hydride to be on the more substituted carbon. So that's the anti-Markovnikov. And the second step would be to get rid of that BH2 and oxidize it, and that's where we add hydrogen peroxide and OH minus. So that's the anti-Markovnikov addition. It's a syn addition, so we're always going to have to add the OH and the H on the same phase. There is a chance that you get the other enantiomer, obviously, if that structure is chiral. The two other reactions that are Markovnikov, one of them is going to go through rearrangement, and the other one does not. The one that goes through rearrangement is the acid catalyzed hydration. So when you have an alkene reacting with water in presence of H+, the very first step is the formation of the carbocation, and that's where the OH is going to be attached. Unless that carbocation goes through rearrangement, then the more stable carbocation will be the one that's the OH is going to be attached to. Important to keep in mind, it's a Markovnikov addition that goes through rearrangement. It gives you an alcohol at the end. The other reaction that's also Markovnikov addition, but it doesn't go through rearrangement, that's the oxymercuration demercuration. What is the condition for this reaction? Two steps. The first step is mercury 2 acetate water, and the second step is sodium borohydride to get rid of the mercury. So you form a mercurinium ion intermediate. That's like a bridged structure with the mercury positively charged, and the water will attack the more substituted carbon. So you end up making an alcohol without having rearrangement taking place. To review these reactions, go back to the alkene chapter 8. Vicinal diol. So if I want to form a 1,2 diol, depending on what kind of diol am I going to be having, there is access to either of the two. So if I want the syn diol, the two OHs to be on the same phase, I have one of the two options: osmium tetroxide, hydrogen peroxide, or the cold dilute basic potassium permanganate, KMNO4. So either of the two will get me access to the syn diol. If I'm interested in the anti-diol, I'm going to need to form the epoxide from the alkene first. The peroxide will be the epoxide will be made using peroxyacetic acid or peroxybenzoic acid or metachloroperoxybenzoic acid, which is MCPPA. Any of the three will deliver the epoxide. And once I have the epoxide, I react it with H3O+, and that gets me to the anti-diol. The anti-diol is when the two OHs basically on opposite faces. It requires the formation of the epoxide from the alkene. So we could see here clearly how how many methods are actually utilizing alkenes to give me an alcohol, whether it's a single alcohol or a diol. Another access to alcohols can be utilizing basically the organometallic reagents. What's an organometallic reagent? Organometallic reagents when you have a carbon chain moiety and a metal attached to it. Once the metal is attached to a carbon, that tends to make the carbon more negatively charged because the metal tends to be positively charged. We've seen an example of those in the alkyne chapter when we dealt with the acetylene giving me acetylide, and that acetylide is actually an example of organometallic reagent. Additional examples we're going to learn in here, the Grignard and the alkyl lithium. Usually those reagents, they can attack an alkyl halide through an SN2, or they could attack a carbonyl through basically a nucleophilic addition. So we're going to see how that addition, nucleophilic addition, gives me access to alcohol. This is the alkyne being basically deprotonated using sodium amide, and we said back in chapter 9, you cannot form an acetylide using a weak base or a base that doesn't deliver the equilibrium to the right. Because if I would have a hydroxide, the hydroxide will give me water, and the water pK is about 15.7. Alkyne pK is about 25. So the equilibrium doesn't favor the right, it favors the left. That's why we have to use a much stronger base. That's sodium amide or lithium amide or potassium amide. Once that deprotonates the hydrogen, it's going to give me an acetylide plus ammonia. pK of ammonia is 33. pK of alkyne is 25. So we could see how favorable it is to push the equilibrium to the right. And once we have that acetylide, it can go through an SN2, this alkyl halide to be primary alkyl halide or a methyl halide. Why? Because if it's a secondary halide or a tertiary halide, the acetylide is bulky enough to go through elimination rather than a substitution. And that's what's been mentioned actually back in chapter 9. So the alkyl acetylide, once again, attacks a primary or a methyl halide to give you the nucleophilic substitution product. And you can see it here, it becomes basically an internal alkyne, starting with a terminal alkyne. The acetylide can also do nucleophilic addition, attacking a carbonyl of an aldehyde or a ketone. What happens when this attack takes place? It takes place on the carbon, opens up the pi bond. The carbon is the most electrophilic part of the carbonyl. So the pi bond, once breaks up, it gives you the O-, and that O- gets protonated using H3O+ to give you basically the acetylenic alcohol. So it's important to keep in mind that the alkyne is not strong nucleophile, but once I generate the acetylide using a sodium amide or potassium amide or lithium amide, that becomes a very strong nucleophile. Not a strong base, but a strong nucleophile. And that strong nucleophile can attack a methyl X or a primary X to give you an SN2 outcome, or it can attack a carbonyl compound to give you the nucleophilic addition outcome, which is the alcohol. The first example that we gonna generate a lot of alcohol out of is the Grignard. So the alkyne can give me alcohol, but it's an acetylenic alcohol. So I'm forced to have an alkyne unit on the carbon attached to the COH. But in here, the Grignard, it gives me access to straight chain alcohol that could actually give me just alkyl OH. So Grignard, it's a Nobel Prize winner reaction. You start with the alkyl halide, and then you react it with magnesium in presence of ether-type solvents. Ether-type solvents could be diethyl ether, could be TBME, terbutyl methyl ether. Any of those ether-type solvents can be used in these reactions. Now, this reaction is very sensitive to moisture and to air. So that's the reason behind using ether-type solvents. They form more of an insulation around the Grignard reagent, protects it during the course of the reaction. Now, keep in mind, Rx is a it usually acts as an electrophile. Once I react with magnesium, it's going to give me RMGX, becomes a strong nucleophile. So you're going from an electrophile to a strong nucleophile. And that's the utility of this reagent, is to use it as a nucleophile in a lot of reactions, one of which is to make an alcohol. So whether I use magnesium or lithium, as I see in the following example, I'm going to be having an RMGX or R lithium. Both of these, you will have the carbon attached to the metal, negatively charged, the metal positively charged. And that's important to keep in mind. Iodides are usually very reactive, so that's why they tend to not use them, but it's easier to control the reaction when we have an RXX is Cl or Br than iodide. Fluorides usually are very, they don't react, or very, very slow in reactivity, so they tend not to be used either. So you could be having a primary, secondary, or a tertiary alkyl halide, and you will still gonna generate a Grignard out of. So once again, Grignard reagent is referring to the RMGX. How do we make it? We start with RX, reacted with magnesium in presence of diethyl ether or any ether type solvent, and that gives me RMGX. Here is examples. So I have a phenyl halide, that's phenyl bromide, plus magnesium, that's going to give me phenyl magnesium bromide. Here is the sick butyl chloride with magnesium in presence of ether type solvent. That's going to give me basically the RMGX, a Grignard reagent. And the reactivity, as we mentioned, the RI will be much more reactive than RBR, than RCl, which is way more reactive than RF. So the insertion of the magnesium becomes easier when you have a good leaving group. So, but keep in mind the alkyl magnesium iodide is usually a very reactive. So if the reaction cannot be controlled, then we go back to the alkyl bromide or the alkyl chloride. Organolithium, very similar to Grignard. So in the Grignard, we have RMGX, starting with RX and magnesium. The organolithium, we're going to have R lithium, starting with RX plus lithium. So RX, where X is Cl, Br, or I, same thing, plus 2 lithium. Why is it 2 lithium? Because one of them is going to form an ionic bond with X, and the second one will form basically the bond with R, to make it a negatively charged carbon attached to that lithium. So in terms of reactivity, organolithium and Grignard, they are exactly the same. In terms of solvent type, the Grignard usually prefer to be in ether type solvents. The organolithium, they can be used in any other solvents, but they cannot be product solvents. So you cannot have a hydrogen in those solvents, just like the Grignard, because if you have a hydrogen that can be picked from the solvents such as water or alcohol, then this R minus, that's in R lithium or R magnesium X, can actually pull that hydrogen from the solvent, and it will be a dead end reaction. So you'll end up making an alkane. So you don't want that to happen. So in order for us to keep it R lithium and have it to attack a carbonyl or any other substrate, and the Grignard the same thing, we have to have an A product solvent. In the case of Grignard, preferably to be ether type solvent. And this is a list of examples we can make alkyl lithium or organolithium out of. So here's the N-butyl bromide with 2 lithium in hexane, can give me butyl lithium. This carbon right here, which is attached to the lithium, is negatively charged, where the lithium is positively charged. The vinyl chloride can give me a vinyl lithium. Phenyl halide can give me phenyl lithium. So this is just a variety of functional groups that we can make the organolithium out of. Now, all of these, whether we're talking about Grignard or organolithium or the acetylide, can do the same exact pathway when they see a carbonyl of an aldehyde or a ketone. They're gonna attack the carbon of the carbonyl, and the first point where the arrow is gonna start from is the R minus. So if it's an acetylide, it's going to be the C minus. If it's an Grignard or an organolithium, it will be the carbon attached to the metal. And that's where the arrow starts from. So this is going to attack the carbonyl carbon, opens up the pi bond. So that's going to give me an alkoxide. So you're going to have a second step. That's H3O plus to make that O minus OH. If the interest is to make an alcohol, you're going to obviously have to have a second step. That's H3O plus. So it's always going to be two-step reaction. Whatever one you're using, acetylide, Grignard, or organolithium, you're going to have that first step to be done using the organometallic reagent, and then followed by a second step, that's H3O plus, to get to the alcohol. And that's important to keep in mind, that alkoxide will not be protonated unless you throw in H3O plus or water, preferably to be H3O plus, so you can push the reaction to the right. Because you don't want to have two pKa of almost the same, water and alcohol almost the same. So it's best to push it to the right by having H3O plus to be the protonating agent. You could see here, when you react Grignard or organolithium with formaldehyde, you're going to have access to a primary alcohol. If you have an aldehyde, you're going to have access to the secondary alcohol. If you have a ketone, you're going to have access to the tertiary alcohol. So I don't have to memorize those. All what I need to keep in mind that the point of attack is going to be the carbonyl carbon. And once that R group is added to that carbon, you're going to end up making an OH. So the resulting structure, if it's a primary carbon, obviously it's going to be a primary alcohol. If it's a secondary carbon, it's going to become a secondary alcohol. If it's a tertiary carbon, it's going to become a tertiary alcohol. So that's all what I have to remember. Now, remember, in all of these reactions, you're going to have a second step that is H3O plus. Do not put the same arrow for that reaction to have both Grignard and H3O plus at the same time. You have to have the numerical steps highlighted, because H3O plus with the Grignard, if it's the same step, it will just convert the RMGX to RH, and that's the alkane. End of story. You're going to have the second step written to be H3O plus. So here's the aldehyde. So the first case is the formaldehyde. The second is the aldehyde. So you already have an R prime in there. And once you add the R group, it's going to become an alkoxide followed by H3O plus to give you an alcohol. So R prime R, so that's a secondary carbon. That's why this is a secondary alcohol. Here's another application of the Grignard. So you have the Grignard or the organolithium. Again, R lithium or RMGX will be the same exact reactivity. Once this reacts with ketone, the ketone has already R prime and R double prime. When you have this R group added, now you have a tertiary alkoxide. So that carbon that has the OH is tertiary already. That's why it's a tertiary alcohol. Here's a synthesis question. It's asking you to basically make this compound. It's a tertiary alcohol. So you know you're going to start with a ketone and Grignard. Now, the ketone can have cyclopentyl and ethyl on it, or it could have methyl and ethyl, or it could have basically the cyclopentyl and the methyl. Whichever one you do, you're going to get the same point at the end. But you have to remember, you have to have an H3O plus as a second step. So you could do the cyclopentyl methyl ketone, you could do the cyclopentyl ethyl ketone, or you could do the methyl ethyl ketone to be the ketone structure. As a result, if you use the cyclopentyl methyl ketone, you're going to end up having the Grignard to be the ethyl magnesium bromide or the ethyl magnesium chloride. Doesn't matter what halide you use. If you end up using the route where the cyclopentyl ethyl ketone be the ketone, then you're going to have a methyl magnesium halide. If you use the ethyl methyl ketone, then you're going to have the cyclopentyl magnesium bromide to be the Grignard reagent. Now, yes, the three of them are acceptable, whichever one you use, but the question is asking for a route where the structures to be used to be no more than 5 carbons. no more than 5 carbons. So that limits your choices actually to only one, because the first one it has 7 carbons, the second one has 8 carbons. This one has 4 carbons ketone and 5 carbons Grignard. So you know that if the question is limiting you to number of carbons to be where each reactant has to be, then you're going to have to consider that when you propose a synthesis route. And that's why the answer, actually the appropriate answer for this question would be the use of ethyl methyl ketone and the cyclopentyl magnesium bromide. How do we make the cyclopentyl magnesium bromide? Using cyclopentyl bromide plus magnesium in ether. And that will give me this Grignard. Once these two react, I'm going to form the alkoxide, and that's going to be followed by H3O plus to give me the alcohol at the end. We will learn additional methods using Grignard, how to form alcohol out of. We will also see reduction of carbonyl, how it could give me access to alcohols as well.